Hello, today's video is on parallax. This is one of many videos on the series about space, astronomy. So let's get started. So parallax, before we get into parallax, this is for Edexcel only. The two specification point linked to Edexcel. Now, before getting into parallax, let's just understand some basic terms. Luminosity. Now, luminosity in terms of stars or any object for that matter that emits any light or electromagnetic waves, it is the power that is emitted by the object. For example, as you can see on your screen, a 100-watt bulb, the luminosity of a 100-watt bulb is 100 watts, a 50-watt bulb is 50 watts. It's the power which is actually emitted by the star. Now, so as with any other physical quantity, it's just another name for the power, but because it is a power emitted in the form of radiations, we call it luminosity, and it is measured in watts. Okay, now brighter star, higher luminosity, not always. If you have a star which is closer to you and a bigger star which is farther away from you, so this is V on Earth, this is a star A, and this is star B. Now, this has, as you see, is not the luminosity. What this emits is luminosity, but what we see is not luminosity. So if I say that star A is brighter, so it should have higher luminosity, no, I don't know that. I don't know that yet. So how to know which star has higher luminosity? We came up with something called as intensity. Now, as you can see on the diagram in your board, in your screen, so this is, let's say, a 100-watt bulb. If a person is standing here, he or she is receiving a lot of brightness from this bulb. Energy is received in this area. But if you move to a distance d equals to 2, the energy received becomes 1/4. So as you double the distance from the source of light, the energy received per second decreases to 1/4. And similarly, if you move to 3 times as much distance, then the energy received becomes 1/9. So the energy that we are receiving is called intensity, and that depends on the distance from the source of light. So we define intensity in units as watts per meter square. So what's happening is, if I draw this bulb here at a distance d, the entire light coming out from the bulb is spread in a sphere of radius d. If you double the distance to 2d, it is spread in a sphere of, it's spread in a sphere, not a circle, okay? It's three-dimensional. It's spread in the sphere of distance 2d or radius 2d. If you make it 3d, it would spread in a radius of distance 3d. Okay, I don't know why subtitles have started. Okay, is this okay? So we define intensity as luminosity is the light which the star is emitting divided by the area in which it is spreading. It's not the area of the star, it's the area in which it is spreading. This area, so the whole sphere. So as you can see, luminosity is in watts, distance is in meters square, so intensity is measured in watts per meter square, and that is why it is also called as inverse square law, because intensity is inversely proportional to distance squared. So if you double the distance from a star, the intensity that we receive becomes 1/4. So now going back to this one, we said the brighter the star, higher is the luminosity. Now, what we are seeing the brightness. So we are seeing what? We are seeing intensity. And does the intensity directly tell you the luminosity? No, intensity not only depends on the luminosity, but also depends on the distance between the U and the star, 4 pi distance squared. So if this star is appearing brighter, but then it's also closer, this could have higher luminosity, but it's still appearing weaker because it might be farther. So intensity is the light that you perceive, is the brightness that you see. Luminosity is the brightness that is emitted. Now, light years is generally the units we used for distance in astronomical terms, because in astronomy the distance is so large that you cannot be measuring in meters or centimeters. So it's a unit of distance, and it is the distance traveled by light. So it's the distance traveled by light in 1 year. And we can always calculate that, but it's there in, no, you don't need, it's not there, you have to calculate it. So 1 light year is then speed of light. What's the speed of light? That's given in your equation sheet, 3 times 10 to the power 8 times 1 year is how many days? 365. 1 day is 24 hours. 1 hour is 60 minutes, and 1 minute is 60 seconds. So that gives you 1 light year. Okay, so 1 light year is this many meters, and you can use your calculator to work it out. Now, simple questions, pause the video, try to do it yourself, or let's do it together. Again, the ideal situation is that you pause it and do it yourself. Now, the luminosity is watts and intensity is watts per meter square, or apparent brightness. I don't know why I do have two times. So apparent brightness is 3 times. Oh my god, apparent brightness is nothing but the intensity. So if I write intensity is L over 4 pi d squared, rearranging 4 pi d square is L over I, d square is L over 4 pi I, and then of course my d is the square root of L over 4 pi I. So plugging in, my luminosity is 5.9 times 10 to the power 32, then divided by, you can just do this in your calculator, times what's my intensity? 7.9 times 10 to the power minus 10. I'll do that in my calculator. Just give me a second. So that is coming as 2.4 times 10 to the power 22 meters. Say, just more use of your calculator. 10 to the power 22 meters. No, sorry, 20 meters. Okay. 2 stars are the same distance from Earth. Okay, so now the distance is same, but their intensities, which is brighter, star A is brighter. So obviously, who has higher luminosity? Now, because the distance is same, whoever is brighter has higher luminosity. So luminosity of star A to the luminosity of star B. So you see, they're directly proportional. So I'm going to write intensity of star A divided by intensity of star B. So this is one of the common mistakes generally the A-level student does, that you do not write in the right order. So you'll write A over B and then you will write B over A. So make sure you write the symbols to tell your mind whose luminosity you're writing first, and then plug in the values. Go back to the formula, see whether it's directly related or inversely related, and then just plug in the values. Minus 13. Okay, using my calculator, this is 8.9 divided, sorry, 8.9 divided by 2.9, which is approximately, I'm getting it as 30. So the ratio is not 30, 31. So this is 31. So 31 times. Okay. Now, how do we measure such distances, such huge distances? How do I know star A and star B are at the same distance? So for that, we have different methods, parallax methods, then we try to use standard candles, then we use Hubble's law, redshift. There are different methods. So, but first, we need to note this. What is an astronomical unit? So clearly, the distances are very large. See here, the distance is so large that we need to come up with bigger units. So one of the bigger unit is light years. Another standard unit is astronomical unit. Now, we assume that the distance between sun and earth is 1 astronomical unit. That's the definition of astronomical unit. Distance between sun and earth is 1 AU or astronomical unit. Okay, you don't need to do all this. Okay, where is, okay, so now standard candle. A standard candle is a astronomical object whose luminosity is known to us. We know what is the luminosity of the standard candle, and we also know what's the distance of that from earth. So anything whose luminosity is known to us is a standard candle. The kind that you need to know for your examples of the standard candles. So example is Cepheid stars. I don't know if I'm pronouncing it right. Let's just go back and see the spelling. Yeah, Cepheid, E-I-D. So Cepheid, I'm going to rewrite it. Okay, so Cepheid stars. Okay, they were discovered by Hubble, as you can see. I've written it here in case if any one of you are interested, just pause the video and read through it. You don't need to know this for your exam, that's why I'm just zipping past through it, but they just give you a background how all of that came. But for your exam, you just need to know this definition. What is standard candle? It is an astronomical object with no luminosity and is used to find the distance from the earth. You need to know one or two examples. One is Cepheid stars and one is type 1a supernova. So we know their luminosity and then we use it to calculate. Again, I've written the spelling wrong. And we use it to calculate the luminosity of something which is unknown to us. Now see, the idea is same intensity as you go away from the stars or an object of known intensity, known luminosity. If the distance doubles, the intensity becomes 1/4, distance becomes 3 times, intensity becomes 1/9, distance becomes 4 times, intensity becomes 1/16. So it's the same inverse square law, but it is used to measure the distance from Earth and it is an object of known luminosity. Now, for the next method, which is parallax method, we need to know something else, something called as arc second. Now, you know that the angles are measured in degrees, right? But degree is a very big unit again. So for astronomical distances, we divide this degree into something called as minutes. So 1 degree is divided into 60 minutes. That's a symbol for the minute. That 1 dash is a symbol for minute. And then this 1 minute is also very large angle. So we further divide 1 minute into 60 seconds. Okay, this is divided into seconds. So 1 minute is 60 seconds. That's a symbol for seconds. So arc second. So arc second, the symbol is double dash. So that's all you need to know. Now, another astronomical unit for distance is parsec. So far you've done light year. Second was AU. AU is just the standard distance between Earth and Sun, and now parsec. Now, what is parsec? Now, parsec is defined to take care of 1 arc second. So if the angle is 1 arc second, then this distance is called parsec. In meters, I've written it here just to take care of your curiosity, and this is 3.26 light years. So if a star is at a distance of 1 parsec, then it will always subtend an angle of 1 arc second. So if I have an angle of 2 arc seconds, you can calculate what would be the distance d times 2. So that's just to make our life simple in calculations. And the physicists, the astronomers, not astronomers, astrophysicists are busy doing lots of calculations every day. So this is just to ease their life and make their calculations easy. Now parallax. Okay, before I explain this to you, what is parallax, just do one thing. Do me a favor. Stretch your left hand or right hand and stretch your thumb out at your arm's distance. Okay, keep your thumb like at your arm's distance from your eye. Close your left eye and see that thumb, and then close your right eye and see that thumb. So the difference in the position of the thumb as you close your one eye, that shift in the position of thumb is called parallax. Or as you can see in this animation, as something is moving by with respect to the position of the moon, your mountains are shifting distance, your trees are shifting distance. So this shift in the position of mountains and trees with respect to a fixed one, moon at the back, is called parallax. This method is used to determine the position of the star. Now, what you need to know is against the background of a fixed star. So see here, just let me just explain you. So this is your sun, Earth. So Earth is moving around the sun. So at one position and then at second position. So position 1 sees Alpha Centauri at the background of this pink star. And when it comes here, just like your thumb has shifted, it sees the pink star now here. Now, obviously, because this distance is 1 AU, I'm going to make this diagram here. So this is the diagram. So this is sun, this is Earth, and this angle is 1. Obviously, now we are measuring this whole angle. So you'll have to, sometimes this entire angle 2.5 will be given, then you'll have to half it. This is 1 AU. Okay, and now this is the distance from the star. Sun and the Earth will almost have the same distance because this is 1 AU, and generally the distance from the Earth and Sun to the star is so huge, then you can almost take this R as equal to D because the angles are very small. See, I'll just explain you this what I just said. See, this is your triangle, and this is another triangle. What I'm doing is I'm reducing the angle to so low that this height becomes almost negligible. So then this R and D are almost same. So these angles are so less that the hypotenuse and this are almost equal. Okay, now this is, let's say, theta. Theta is very small. So R is nearly, this is a symbol for nearly equal to D. Now I'm going to just write here. So you know your trigonometry. Now can I write tan theta as 1 AU over D? So to calculate D, that is the distance between the star and Earth or Sun, is this. And now because angle is very small, when your angles are small, tan theta is nearly equal to theta, almost exactly equal. So I can write D as 1 AU over theta. That's it. Now, if you put theta in radians, you'll get D in astronomical units. So if theta, Okay, I'm just going to write here. Theta is in radians. Then D is in AU. So 2 AU or 3 AU or 4 AU. So we'll get in terms of the distance. So we'll understand, okay, this is our sun at 1 AU distance, and this particular star that we have just discovered is like 100 AU. So it is 100 times as far as our sun. But condition is that your angle should be in radians. What is meant by the term parallax and when measuring distances to stars? Now, this is kind of an exam question, but you need to figure out what is the meaning of the term parallax. So it is nothing. I'm hoping that you've paused and tried to answer it yourself. So it's apparent shift in the position. So it's apparent shift. So this pink star is appearing to shift. Was your thumb shifting? No, it was not shifting. It was appearing to shift. So it is an apparent means the one that appears to you. So the apparent shift in the position of the star. So this is the star, the pink star is shifting from here to here. So apparent shift in the position of the star as observed from Earth, because now why this shift is happening? Because Earth has moved its position from A to B. So apparent shift in the position of the star against this star when the Earth shifts its position. Apparent shift in a position of star against distant background stars caused by change in observation position, because Earth is shifting its position. Why it is only suitable for measuring distances to relatively nearby stars. Now why can I measure only up to this star? Why I can't measure up to this star or this star? Let me just show you the diagram here, then you can try and answer. Let's say this is your this is your sun. Okay, let's see if I have an eraser here. I do have. Okay, that's good. All right, so this is this Earth, okay, and this is the sun. Closer by, so we measured Alpha Centauri here. So Alpha Centauri, the angle was measured by measuring its shift with respect to some faraway star. But so this is our Alpha Centauri here. Now let's just move on to some distant star here. Can you see what's happening to the angle? See what's happening to this angle? This angle is getting lesser and lesser and lesser. So we do not have that kind of, if we do not have that kind of instrument which can give us an accurate value of this angle. So angle itself is so small, 0.001 radians. Now if this one has, let's say 10% error or 5% error, we are not getting the right values because the values are very small. So why we cannot use it for measuring distances which are far away stars? Because the angles are very small. We do not have instruments which can give you a certainty. There are lots of uncertainty in the answers, and that's why then the distances that would be measured would not be accurate. See, as distance increases, parallax angle decreases. You describe that the angle is decreasing, which I explained you from the diagram. You have to write it. If the angle becomes very small, it's difficult to measure it accurately. We do not have such precise instruments, which is limited by the resolution of telescopes or instruments, which leads to uncertainty in distance for distant stars. So 4-mark answer, you would be writing all of that. If it is 1 mark, you can just write angle is very small. If it's 2 mark, then you can just add whatever the resolution is limited. Okay, all right, let's try this one. Now trigonometry and parallax, I've already explained you how to use it. You just make a triangle. This is the parallax, remember, Earth, Sun, and this is the parallax angle. This is 1 AU. This is the distance D. This we actually are measuring R, but R is nearly equal to D because They are very, very far away. The star is very, very far away, so far away that D is nearly equal to R. And then you use trigonometry. Tan theta is, I'm just doing it once again so that you do not get confused. Okay, and then the rest of the thing you can do when you rewind the video and you can see it. All right. Okay, let's do this exam question. Rigel A in the constellation of Orion is one of the brightest stars in the sky. It is a massive blue variable star with an intensity peak at a wavelength of this much. So we have a peak of wavelength happening at 0.25. Are also variable stars. They're used by astronomers as standard candles, although none of them are close enough for trigonometric parallax to be useful. So they're very, very far. We can't use trigonometric parallax. What is meant by standard candle? So this is an actual exam question, and you're just supposed to tell what is a standard candle. So you need to write an object of known luminosity and is used to measure the distance. Of course, see, that's why they build up that context. Trigonometric parallax is not useful. So you need to specify standard candles are known luminosity used to measure the distance. Now, how do they use standard candles? That's the next point. So we know what are standard candles. Okay, so the first, we know the luminosity of the standard candles. Okay, so what do is we calculate the flux or intensity on Earth. So another word for intensity is flux. So measure the intensity on Earth, apparent intensity, apparent brightness, flux on Earth. Use inverse square law. Inverse square law is I equals to L over 4 pi d square to calculate the distance. Okay, let's see. So standard candles, flux or brightness is measured on Earth. Use inverse square law. Distance to standard candle is calculated or determined. And then the first part, standard candle is an object of known luminosity. Known luminosity is the most important thing for writing in the standard candle. That's the word which is going to get you the mark. Explain why stars have to be within a certain distance. Okay, again the same thing. Why they have to be in certain distance. Now this is a 2-mark question. It's not a 4-mark. So why do they have to be a certain distance for the trigonometric parallax to be useful? Pause and try to write yourself. Okay, so what happens to the parallax angle if the star is too far away? So what is parallax? It's the angle which is measured with respect to the position of the star. It reduces when the distance increases. Okay, is the angle subtended by the star by the radius of the Earth's orbit, or you can just write is a change in position of the star again. So you're defining parallax or you're measuring the parallax angle. If the star is too far away, the angle measured is too small. That's it. That's your parallax. So what you just need to know for this part is what is, you can always read, this is very interesting. What you need to know here is this. How astronomical distances can be measured using trigonometric parallax? You make that triangle, write the assumptions, write the formula, done. How astronomical distances can be determined using measurements of intensity? The last question. Intensity is luminosity over 4 pi d square. Intensity is either measured using standard candles. Yes, standard candles for now. Next time we'll do something else. Standard candles, and then you just relate it to inverse square law, and that's it. So keep revising. Well done for watching. Thank you.